Welcome back to ECE 501B. In this segment, we're going to look at principal component analysis, or PCA for short, which is really trying to determine what is a way to obtain sort of the principal direction of a collection of vectors. And some of this, the beginning, I've already talked about in an earlier lecture, so I'm going to slide through that pretty quickly. And in this case, here's really sort of our first question. If we're given a set of vectors or points in a finite dimensional vector space V with a dimension of, let's say, capital N, what is the shortest list of vectors that can represent this, a generic vector x in this subset of vectors, or in this set of vectors S? As we've talked about before, that depends on what S actually is, and here are a few examples. For example, if we are working with capital N equal to 2, and we have the entire, or the chance of having an arbitrary vector in R2, that's what S represents, then we actually are going to need a two-dimensional list, or a list of dimension 2, in order to represent any arbitrary vector x in all of R2, when S is all of R2. In this second example, though, suppose that we are in this two-dimensional plane, but now all of our vectors lie in just one direction, and let's make it specific. Suppose that it's the horizontal axis x sub 1. Then the principal component is really in that direction x sub 1, and all we need is the length of that vector, or one number a, in order to describe a vector in that particular direction. In this particular example, now S is this collection of points that I've tried to illustrate by red dots, and those points are actually clustered around, let's say, x sub 1 equals x sub 2. If we could now find that line that models x1 equal x2, then really that's the principal direction, or the principal component of that collection of data points. And now, really, if somebody gave us a point in that plane R2 that was supposed to be clustered around x1, x2, we just need to know that direction, and then the distance along that direction would give us that particular vector. And so we would really only need a list that's one long in order to describe a point, or we would just need one number to describe that particular information in that principal component. Now, there's really no perfect short list, but if we're interested in a best short list, this really is more interesting in higher dimensions versus just a two-dimensional example, but the two-dimensional example is easier to draw. Now, if we are in a higher dimensional setting, capital N might be 100, then what basis do we obtain the best k dimension, where k might be 3, maybe it's 6, maybe it's 10, when capital N is 100? We want to know what are these best directions to approximate some vector x that might be living in this higher dimensional space of dimension capital N. And the answer is the principal component basis, or also called the Karhunen-Loew basis. And what that really consists of is finding an orthonormal basis B that allows us to minimize the distance between x and its smaller list approximation, x hat. By that I mean the following. Suppose that we now have identified these in vectors, and maybe what I should say to be consistent with the notation before, let me go ahead and make that a capital N. And now we have found an orthonormal basis B of vectors B sub 1, B sub 2, up to B sub capital N that we can represent any vector in our n-dimensional space with respect to. We can decompose any vector with these inner products giving us the coefficients or the weighting of the vector x in the direction b1, b2, etc. We now want to restrict or find a shorter list that we can then model x by, and we want to now approximate x with a much smaller list of basis vectors, b sub 1 through b sub little p, where little p is less than capital N, and that will then be our x hat. And we want x hat to get as close to x as possible, whatever value of p we select. If capital N is 100 and we select little p to be 1, we want to know what's the principal direction that will allow us to best approximate this 100-dimensional vector with a vector in one direction, and we just need the number in that one direction. For example, if we consider the case p equal 1, which is what I was just talking about, then x hat is just going to consist of this first term, or little p is equal to 1. We now have x hat is the inner product of x with b1. That gives us the amount of b1 that is in the direction of, or I'm sorry, that gives us the amount of x that's in the direction of b1, and we now scale b1 by that weighting value or that inner product. So if x hat is the inner product of x with b1 and scaled by b1, then really the difference between x and x hat is just the tail that's left over, because if you look at what we've done, we're taking now x hat away from x, and now x hat does not contain these pieces, which means that the difference of x with x hat is going to be this combination of vectors. It's going to be x inner product with b2 times b sub 2, and remember these b's are orthonormal vectors, which allows us then, when we look at the norm of this residual that's given by x minus x hat, we will simply have the sum of these weightings or these inner products squared, and that will now give us the, and what we're wanting to do is we want to now minimize this difference between x and x hat when little p is equal to 1. If that's the case, then what we really want to do is we want to minimize the size of this right-hand term or this right-hand expression, but that's the same thing as actually maximizing this piece in our x hat expression. If we could maximize x in the direction of b1, then we will minimize this residual that I've highlighted in blue. What I'm trying to say then is that minimizing the expected value of this norm difference between x and x hat squared, minimizing that is actually equivalent to maximizing the expected value of x with b1 squared, which really means that we want to find a vector b1 that will give us the largest expected value in this comparison with it and x, or correlating it with x. Now to do that with all of the data, let's now try to formalize that. Let's define an operator of projections for each x that we have in our underlying vector space, finite dimensional vector space S. For each vector, let's now take that and stack those so that we convert x into a row vector, and now we have, let's say this is now a vector x, but now we're going to index that, so we're now making x sub 1 this row vector instead of a component in the vector x. X sub 2 is another row vector, and we just keep going, and let's say that we now have m such row vectors. So capital X is actually representing a stack of row vectors, and x is now going to be m tall and n columns wide, meaning the data points that are in each of these vectors x, represented by x sub 1, x sub 2, etc., we have little n data points in each of those. So x represents m vectors in S, with each vector x sub j having a length of n columns or coordinates. So each measurement has little n, or Nevada, elements in it, or coordinates, and we've taken m such measurements. What we wanted to do then, by trying to find the best b1 to achieve this largest value, or maximize the expected value of x b1 for all these different x's, we now are really saying that what we're trying to do is we want to now look at b1 relative to the inner product of b1 with all of these measurements, little m measurements. Let's say that result is now p. So this now looks like this inner product of x1 with b1. b1 is just a column vector, x1 is a row vector, x2 is another row vector of a second set of measurements, and we keep doing that for all of the measurements, little m measurements, and we're calling that result x1 b1 is just going to be a scalar, x2 b1 is going to be a scalar, and we're just stacking those scalars into a column vector that we are calling p. This capital X b1 is really then just a stack of inner products, in particular little m such inner products, where x sub I b1, as I said, represents an individual inner product. again, what we're wanting to do is we want to maximize the resulting vector. We're trying to pick B1 such that it aligns as best we can with all of these measurements, x1, x2, x sub n, which means we want to maximize all of the coordinates in this column vector P. And we can do that by maximizing the square of its norm, where we're now saying that this norm of P squared is really just the sum of each of these coordinates in P squared. Now let's look at what that represents if we start redescribing P in terms of how we defined it, which was capital X B1. The max of the norm squared is really just the max of this vector times itself, or P transpose P. But another way of writing P is xb1. So now if we have xb1 transpose, that's P transpose times P, which is xb1. We now want to maximize that particular expression. We know x, we don't know b1. We're trying to find the best b1. Well, if we rewrite that by taking the transpose, we now have b1 transpose, capital X transpose, capital X b1. And what we are going to do now is we know this x, so we know it's transpose. Let's go ahead and call this matrix, capital X transpose X, let's call that R, which means that we now are trying to maximize, by the choice of B1, this expression, B1 transpose R, B1. Now remember what we know about certain matrices. If you look at R, which is X transpose X, we're assuming that that X was made up of real numbers, so it's actually self-adjoint because it equals its transpose. And if we have a self-adjoint matrix, then we can find a basis for that matrix in terms of its eigenvectors. So, and those eigenvectors are actually orthonormal, or they can be made orthonormal. So if R, which is X transpose X, is self-adjoint, so it has a basis of eigenvectors, and we're going to call them E sub I. Now, if R has a set of basis vectors E, let's go ahead and now decompose B1 in terms of those basis vectors. Let's now let B1 be A1, E1, the component of E1, or the component of B1 in the direction of E1 is A1 times E1 plus A sub 2, E sub 2, etc. down to A sub n, E sub n, where we are now saying that these E's are eigenvectors of R. Let's now look what happens when we decompose B1 in this particular basis that we've selected. Now what we want to do, remember, is to maximize B1 transpose R, B1. If we now write that out, in terms of this decomposition of B1, we now have A1 E1 plus A sub 2 E2 up to A sub n E sub n transpose. That's actually, remember, just B1. Then we have R times B1, but R times B1 is R times this decomposition of B1, which is R A1 E1, R A2 E2, etc. And those are simply R E sub i's are this matrix or operator times its eigenvector, and that's then equal to the lambda sub I E1. So we now have lambda 1 A1 E1 plus lambda sub 2 A2 E2, etc., up to lambda sub n A sub n E sub n. Where this now is actually RB1. With that information, we can now rewrite this product of two terms as simply, and the E1s, remember, are orthonormal, so that we now have this maximum of simply lambda 1 A1 squared plus lambda sub 2 A sub 2 squared plus dot 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 plus lambda sub n A sub n squared. Again, the E1s by themselves are 1. When they are multiplied by each other, they're 0. And we also know that we can have all of these A sub i's to be normal. I'm sorry, to be normalized, so that we're now looking at just a normalized decomposition of B sub 1. Or another way of thinking of that is now we're forcing B1 to have a norm of 1, and that's okay. We're just trying to find the best direction for B sub 1. And we can do that by normalizing these coefficients to give us a magnitude or a length of B1 of 1. What we want to do now is, with this particular expression of max lambda 1 A1 squared plus all the way down to lambda sub n A sub n, we now can maximize the above equation by setting A sub I equal to 1. For the A sub I, associated with the largest eigenvalue, lambda sub I, and consequently set all the other lambda sub j's or I'm sorry, alpha A sub j's equal to 0. And really, there's no loss in generality in saying that we've ordered these e's so that the largest eigenvalue is actually lambda sub 1. If we assume lambda sub 1 is the largest eigenvalue, then the optimal choice for b sub 1 will actually be b1 equaling e1, which is the eigenvector associated with or corresponding to the largest eigenvalue, lambda sub 1. In the notation that we've been using, then, b1 was written as some linear combination of e's. We're now saying that it's actually just going to be in the direction of one of those eigenvectors, and we've ordered those eigenvectors such that e sub 1 corresponds to the largest eigenvalue. Now we can just set b1 equal to a sub 1 e1, and we said that we were going to pick a sub 1 to have a value of 1 and all the other coefficients to be 0. And if we actually, so that's what would happen if little p was equal to 1. If we wanted to try to find the principal component, then we would simply look at the largest eigenvector of R, which is this self-adjoint matrix capital X transpose X, and that would then give us the principal direction or principal component associated with all of those measurements, x sub 1, x sub 2, x sub n, or x sub m. If we need to keep looking at additional directions, if we need more components, in this approximation of x by x with x hat, then we can repeat this process for other b sub i's after removing the e's or eigenvectors of the largest that we came to first. After removing e sub 1, e sub 2, etc. up to e sub I minus 1 from the process. So that's going to give us this set of directions, b sub I, that actually help us minimize the error between x and x hat, where this b sub I is now a set of vectors, b sub 1, b sub 2, etc. That's a set containing however many vectors or principal directions we wanted, which we were labeling as capital K before, so that might be 3, maybe it's 4, maybe it's 1. That's the set containing the K vectors that are desired for the minimum between x and x hat. Now sometimes this may seem a little bit abstract, so let's go ahead and see if we can illustrate this by means of a numerical example or illustration that we can perform in MATLAB. So what I'm going to do is I'm actually going to generate some random components, and let me just go ahead and generate 10 such random components for each direction, and I'm going to just play in a two-dimensional direction. So this is now a horizontal component x that's going to have 10 different values, and I'm simply going to sort of randomly select those 10 points around a nominal value of 1, and let me check or do the y direction in a similar manner, the random variable. So now I have a set of two-dimensional points and I have 10 of those. If we wanted to sort of see what we have, let me generate a scatter plot of those 10 points of x and y. So this is now this collection of points that are scattered, but if you look, the axes are sort of going from 1 to 2 in both horizontal and vertical direction, and they are somewhat then scattered around this 45-degree line where x is equal to y. And that's really sort of our principal component. Let's see if we can actually find that with the technique that we've described just before doing this numerical illustration. So that now my X matrix is actually going to be a column of the X points and a column of the Y points, so that each row here becomes an XY pair. So this is now going to be how I will define the matrix containing the data. And maybe I don't want to display that, so let me go ahead and hide that piece of information. I can now build up the self-adjoint matrix. That's now this X transpose times capital X. And capital X, remember, was 10 rows tall, but it's only 2 columns wide, which means that this self-adjoint matrix R is 2, it's capital X transpose, so that's now 2 rows tall and it's 2 columns wide. And if we now compute this self-adjoint matrix, it's some 2 by 2 matrix. Let's now find, because now we want to find the principal components of R, let's now look at the eigenvector and eigenvalues of R with the eig command in MATLAB. So this is now going to be computing the eigenvectors and eigenvalues of R, or the self-adjoint matrix. We now need to find the direction associated with the largest eigenvalue. The largest eigenvalue is obviously 55 in this case. The smallest one is 0.75. So we now need to get the second vector, or the second column in evec R, to be our E1 that we had labeled before, so in our description. So we now want E1 to be this eigenvector, and these are orthonormal eigenvectors since R was self-adjoint. We now want evec R's second column, so we take both rows, but we keep the second column, and this now is the, or we are now going to extract the second column of evec R, which is the largest, the eigenvector associated with the largest eigenvalue. And that's what we wanted to do. Now let's pull off the two coordinates. Let's call the first coordinate of E1 x1. That's the horizontal direction. So that's now going to be E1, 1, 1. and the y-coordinate is going to be the second coordinate in E1, so that's now 2, 1. Those are now our coordinates of the principal component. And we're defining those to be x1 and y1. So this is now where we are defining the coordinates of the principal component. And if we now put that on the same axis of that scatter plot before as a line, let's now draw those points from the origin to x1, y1. We can do that by saying go from, or here are now our x coordinates. We start at the origin in x and go to x1. We start at the origin in y and go to y1. This should now draw a line, so this will show the direction of the principal component with this set of data. And that's now, you can see that that is the direction of that scatter plot from the origin out to this distance of 1 away from the origin, but that is in the direction of the principal component